Nice haircut.
Okay, so far, what is that we cover? We cover linear motion, right? And the idea is to describe an object that is moving at a certain, speed and is changing position, right? If it's at rest, it is not moving at all, so it's, and this, one other thing we discussed last time is that, motion is relative, right, to the environment, right? So, the first formula that we came about was the average velocity, right? And that is the displacement over a time, right? So if the motion is linear and is uniform, the implication is that, the velocity, meaning the rate of change of its position, is a constant, okay? And how do we describe that? We come up with this formula that the position is going to be the initial position plus velocity times time. Okay? This is a situation where there is no acceleration there. All right? If we have acceleration, the average, the definition of acceleration is the rate of change of velocity, right? The definition of velocity is the rate of change in position. Right? Something is moving, its position is changing. It's changing at a constant pace, so velocity is constant. Now, if this change is not at a constant pace, so if every second the position is changing, right, is increasing or decreasing, right, then implies that we have some sort of acceleration. And acceleration is the rate of change of velocity, okay? So it's delta V, delta T. And from here, we come up with another equation that is going to be V final is going to be V initial plus AT, okay? Here, average velocity can also be written like V final plus V0 divided by 2. Like it's the average, right? Average of two numbers, we add them and we divide it by 2. So from here, we came up with another equation now that involves not only the velocity, but now involves also the acceleration, right? We are able to, from these equations and this equation here, we came up with this one. And last class, I also showed that V final squared minus V initial squared is equal to 2 times A and the delta x, right? If you want to relate the velocity with acceleration and the displacement. Do you guys remember? We came to this formula, right? You remember that?
Yeah, last week.
Yeah, last week, right? So I'm just putting down here the formulas for linear motion, right? So we have constant velocity, we have velocities changing, and we have the acceleration, and then we have this formula. Now, this is a linear motion, and let's see, I have a car. I have a car here. And the car is moving and is going on a straight line, okay? Now, if I want the car to curve, what do I need to do? I want the car now that's coming on a straight line, or any object. I have this object that's coming on a straight line, right? And I want that object to change its directions on a curve. What do you think we need to do?
Change the force to make it go that way?
Change
Or
what?
give it like another, because if going straight, that means it has, there's a force pushing it forward, right? When there, or, I don't know how to explain this. I had it in my head, but I lost it now.
Yeah, no, let's think about Newton's first law, right? The object is moving, right? It's here, and I give a push, and now it's moving continuously, right? There's no force anymore. I just gave a little push, and it start moving. It's at rest. I give a push, and it's moving continuously, right? There's no force to maintain that motion. There is no force there, okay? Because it's going at a constant speed. Newton's first law, an object at rest is not going to start moving until I apply the force. So I apply the force, but I'm not applying anymore. So that means now that velocity is going to be constant and linear, right? Continuously.
So you need to
And
add
there is no
another
force there. It's not moving because there is a force. It's just moving, right?
So you need to add another force the other way, for it to turn.
Yeah, in order to stop, I need to add another force. But in order to change its direction,
You need to
right,
add-
because now here is changing its direction,
If the force is the other way,
I have to apply another force, right? So let's say I'm here, I'm sitting here, right here in the center, and I want the car to do here, so I'm going, what am I going to do? I'm going to, put like a rope or a wood or something here, right here, and I'm going to force the car to go around. Right? So I'm going to force the car to go around up to here, and here at this point I will stop. What do you think is going to happen?
it's going to go straight.
Now it's going straight in this direction. Okay? So there has to be a force. There's no negotiable, right? And even if the speed, I'm not talking about velocity now, I'm talking about the speed, has the same magnitude, okay? I don't want to change the speed, I just want to change its direction. Is that okay? So circular motion, it doesn't happen by itself, right? You can see here, this is a perfect linear motion here. I can say velocity here because it has a direction. Right? But I want to change this velocity and maintain the magnitude of it. So, if it's going 60 miles per hour going east, right? I want now to turn, but maintaining the speed, and when it comes here, at this point where I release the car, is going to continue now on a straight line, right, with the same speed that was here. It's just that now it had this region here that it turned. And in order to turn, do we all agree that it has to be a force? Right? Otherwise,
It can be the force of obviously when you drive, it's the force of the acceleration of the car. That goes this way.
yeah, to go turn, right? And, it has to have, a okay? So now let's discuss that and see how that's gonna look like. So, so I'm gonna draw here a circle, right? And the circle has, a radius, right? And going here, so I have here my velocity, and at this point here, the velocity is there, but the magnitude here is the same, because this, we are talking now about uniform circular motion, okay? Later, we're gonna talk about non-uniform circular motion, and that is when this speed here, right, is changing not only direction, but also the magnitude, okay? Two things here. First, we're gonna start with this idea that this thing is going around at the same speed, right? So the velocity is changing its direction only, okay? So, so here, this, from this position to here, there is an angle here, right? So you want to describe that. The same way, when we had the linear motion, right? I have one, start at this point, and then 1 second, 2 seconds, 3 seconds, right? And I could take a picture, all right, of the car moving, and we saw this is a constant pace, right? Now here, if I take a picture, 1 second, 2 seconds, 3 seconds, right? You have to imagine that this is 1 second from here to here. The 2 seconds is going to be another position here, and this angle is going to be what? The same or different? The first second, you move this angle theta. The second is going to move the same angle, right? So the angle here is changing, right? So the position on the circle, right, or the object is changing every second, and the angle here is going to be the same. Okay? So if I have here my vector, one vector this way and the other vector this way, so that E. So there will be a change from here to here. You see that? If I bring this guy down here, I just brought this vector down here to this position, and what was the change? So this is initial position. Do you see that? That this is the initial position, this is the final position, right? The vector is changing direction, right? Vector is going this way, and then as it changed, it has shifted, right? The vector is going this way, and then 1 second later, it shifted that way. So when I bring this vector to this one, I want to calculate the change. So what is the change from this vector to this one? The change from this vector to this one is this one, okay? And this is delta V. Do you understand that? I have a vector here, move 1 second later, move this way. I brought it here, so the change is from here to here. That's delta V. Okay? And it takes time to absorb that, right? So when we were in the linear, right? The car start moving here, and 1 second later is here, 1 second later is here, right? And if the velocity is constant, right? Here, this is linear motion now. We talk about linear motion. Velocity is constant. What is delta V from point 2 to point 1? linear motion, constant velocity, what is the value of delta V?
Which one, for where?
Now, I'm talking about linear motion here. Uniform linear motion, velocity is constant. So what is the delta V between 0.2 and 1?
It's one.
Velocity is constant, it's not changing. Delta V is V final minus V zero. What is delta V?
So it's one. Delta, like it's two. Oh no.
This is 1 second, 2 seconds, 3 seconds. So velocity here is the
Oh,
same.
it's zero. No, it's zero.
Zero, right? Delta V is zero. Because, we talk about the same direction, right? Now here, delta V is a vector, right? Here is a vector too, but because it's the same direction, I could even say the speed, right? The speed is the same. So V final minus V initial is zero. But here we have a vector. It is the same magnitude, right? It's the same speed, but the direction is different. So delta V is another vector, right? In this direction. So from here to here, the delta V is going in this direction here, right? To the center. Is pointing to the center of my circle. It's like I have here, I bring this guy here now, right, like this, right? It's the same magnitude, so delta V is here. Delta V is here, pointing to the center. And this here is an angle, right? Is this okay?
And it's the same angle.
Hmm?
It's the same angle.
It's the same. What is the same?
It's the same as it's a data. The same data, no? From on the circle.
On the circle, yeah. The same as here. This angle here is the same also, right? That's why I put data here. Right? Now, R is also going this way, and R now is that way, okay? This is also R, and then R. It's changing, right? R is here, pointing to this position, right? And then move that way, okay? The vector, right, of the position is pointing that way now. So delta R is also pointing this way. So I can make a proportion here, because those are two triangles with the same angle, right? So I can make a proportion. I can say that delta V over V is going to be delta R over R. Okay? Is this proportion okay? Like, two similar triangles, right? I can correlate their sides, right? So if I have a triangle like this, and I have different sides, right? So this side, let's say x1, this is x2, this here is y1, this here is y2. So x1 is the same as x2, y2, right? The proportion, because this is similar triangles, right? This good? So this here is the same. That's all I've done here. Those are two triangles that have the same angle, right? So I can write this proportion. Okay? Now, if I want to, because if this thing is moving, right, it's changing its directions, we know there has to be a force there, right? Using Newton's first law, there has to be an acceleration there. Do you guys agree with me? And this force that is making this thing going around, right, is pointing to the center. So this acceleration is going to have a special name called centripetal acceleration, right? Centripetal because it's pointing to the center. Now, how can I calculate acceleration here? What is the formula for acceleration? The definition of acceleration is delta V over delta T. Right? Does anybody has any suggestion how can I find acceleration here? What do I need to have here? I have delta V, I have V,
You have time.
but,
You need the time.
the time. So can I divide delta T on both sides of this equation? Remember, whatever I do on one side of the equation, I need to do on the other side of the equation, right? So I'm going to write down delta V, I'm going to write down here, okay? So delta V divided by delta T, okay? And I'm going to put here 1 over V. And here I'm going to put delta R divided by delta T, 1 over R here, okay?
I have a question, sorry.
Yeah,
Can you explain to me again about the delta V over V and delta R over R?
this here?
Yeah, can you explain that to me very quickly?
Sure, yeah. This is key, right? If you don't understand that, you know. So, on a circular motion, uniform circular motion, right? We know we have this object that has a velocity going that way, right?
Yeah.
And then it moved to, this is position 1, this is position 2. So the same velocity that was going this way now is pointing this way, right? It's the same speed, the same magnitude, but the angle has changed, right? Now, the change is delta. So if I bring this vector down here, I brought, this was the initial vector, and I brought the second vector down here. The angle here is going to be theta. It's the same thing. Okay? Because look, this is perpendicular, this is perpendicular. When I brought that down, so this angle is the same. Now I'm asking, what is the change in velocity? Right? The only change here is direction, right? But it's still, it's not the same vector. That's why we have these quantities in physics called vectors. Because in order to describe this, we can't just describe with speed. If we were just talking about speed, there would be no change from here to there, right? The speed is the same. But direction has changed, and we need to describe that. So when I put that here, delta V is from here to there. So this side of the triangle is the ratio of this side of the triangle by this one is going to be the same as the position, right? This is the displacement. The position is this way, has moved to that way, so the displacement is delta R, right? The change.
So that's like tangent theta is delta V over V, and it's also delta R over R.
Yeah, so those are two similar triangles. The same way I remember I made that little drawing here. There's similar triangle, so the ratio of delta V over V
It's the same.
is gonna be delta R over R. Okay? Now I have this, and I know in order to have this thing move on a circle, I need to apply a force. Newton's first law says that unless you apply an external force, right, things do not change. I have the object, I give a push, and it's going to move continuously at a constant speed. Because something is moving does not mean it has to have a force. Okay? That's Newton's law. And something, to start moving, you have to apply a force. But once it starts moving, it's going to be continuously. If I continuously apply a force on that object, then it's not going to be uniform motion anymore, right? Because if I continuously apply a force on an object, on a linear motion, that object is going to increase its speed, right? The speed is, the rate of change on the speed will be related to some sort of acceleration. So then it's not uniform anymore, it's accelerated motion, right? If we want to describe an object that is being accelerated, right? That's what happened. There is a continuously application of some sort of force in order to keep accelerating, right? So, now I want to figure out, because remember, now our study today is about describing circular motion, right? So I'm trying to come up with some equations that are going to describe that, and here I have this relationship based on this geometry here, right? I got this relationship, but I want to come back to my definition of acceleration. Is delta V over delta T. So how can I get the acceleration from here? So I divide the delta T on both sides, okay? So delta V over delta T is the acceleration causing this object to go on a circle. And because this is pointing to the center, right? We're gonna call this acceleration centripetal acceleration, okay? So this is my acceleration here, and I'm gonna call this AC for centripetal. Now, what is this guy here? Delta R over delta T. What is this? Delta R over delta T.
It's the change, it's one.
The rate of position over time.
But it's I see the
Position is changing over time. What is that?
That's velocity.
Velocity, exactly. Velocity, so I have velocity here, right? Velocity here, velocity here. So this accelerate, I'm going to move this V to the other side, right? Cross multiply here, right? So when I do that, it's going to be V squared over R. Is that okay? So here I have acceleration, centripetal acceleration. This is V, V over R. I have another V here. I move this V to the other side. I multiply V on both sides to get rid of this one, right? Then I'm going to have V squared over R. So this is now my centripetal acceleration. And if I want to calculate now the centripetal force, can you tell me what the centripetal force is going to look like? what is the force? You have the acceleration. What is the force?
Oh, the mass.
Force is what?
Mass.
Force
Mass
is
times
equal
mass.
mass
Acceleration.
times acceleration, right? But acceleration is centripetal acceleration. So force is going to be mv squared over r. So this is the formula for centripetal force. I'm going to put C here, F of C. Is that good? Pamela, what do you think?
It's a lot.
It's a lot? Well, I'm recording, so you can
Go back.
review, go back and watch it.
By when do you post these?
Yeah, I'm gonna post it tonight, because it takes time to, you know, convert it to the computer and then make a YouTube and,
Okay.
but, you know, this is gonna be there. Now, let's talk about this here, right? What is the circumference, right? How do I relate the length? The circumference is equal to what? So C is equal to what? What is the formula? You guys remember the formula for circumference?
PR2,
Yeah, 2
pi2.
pi r, right? Okay, so, but 2 pi is the whole, is like from here all the way to here, right? Now, if I just go some distance, right? So this is the length from here to here. So S is going to be equal to what? Theta r, okay? It's 2 pi is the whole circle, right? Now, if I'm talking just about one arc here, with the distance S, right, it's going to be all that, right? Now, if I want to describe how this thing is moving this way, right? How is S changing? R, is R changing? Is the radius changing? No. But the angle is changing, right? So this is the relationship between this distance and the angle, right? Now, if I want to see how this thing moves, I'm going to see the delta S divided by delta T is going to be a delta angle divided by a delta T times R. Is that okay? Do you guys see what I'm doing here? So I have the whole circle. The circumference is 2 pi r, right? If I have just one arc here, right? And I call this distance here S instead of C, because C is the whole circle, right? I'm just going from here to there. Then it's going to be S is going to be equal theta, the angle, times the radius. The same here, right? Theta here is 2 pi, is the whole circle. I have completed the whole circle, right? So, what is delta S, delta V? Delta T, right? Delta S, delta T is the speed, right? The speed. Right? The tangential speed. So because this thing here is going this way, and this here is going that way, right? So this is how this thing is moving here. How fast is this thing moving here, right? Now, what is delta theta divided by delta t? What is that? You see, when we talk about linear motion, we talk about linear displacement, right? That is the speed. Now here, we talk about an angle, that is changing, right? That is the change of the angle, right? The speed of change of the angle, right? The rate of change on the angle to delta t, that is what we call the angular velocity, right? We call that omega. And that is time r. Is that okay? Do you guys see how this formula is coming from? Right? Now, I can plug that in here. You see that? I'm going to plug this formula, WR, V is equal to WR, right? This is the velocity, right? The tangential velocity. Omega is the angular velocity. R is the radius, right? So, you can see that, if I plug that in here, the square, it's going to be M W square R. Do you guys see that now? Formula for centripetal force is equal ma. That's Newton's second law, right? Force is proportional to acceleration. This is the centripetal acceleration, v squared over r. We know v is related to wr, and when I plug that in here, so I have this other form. So what would be a word problem? A word problem is I can say, well, something is going on a circle with the angular velocity in radians, right? The angle we measure in radians, and at the radius 10 meters or whatever, right? So you just plug in here and you can calculate your force. Okay? Now, let's also talk about, here. This thing is going around and around, right? So, omega, the angular velocity, is the time it takes to go all around here, right? I can calculate that also, right? Is 2 pi, right? That's the angle, 2 pi, right? If I leave this point and I come back here and I clock the time it takes to complete a full circle, that time, we call that the period, okay? So it's 2 pi, is the whole circle, divided by time, okay? That's the period. What is the period?
How do you say it?
Period,
Period, yeah.
period. Okay? Period, right? Is the time to complete a full cycle. Go around. I started here and I time that. When it comes here, that is 1 period. Okay? Now what is frequency? Frequency is how many cycles per second, right? If t is the period is for 1 cycle, right? Number of cycles, frequency is going to be 1 over t, right? How many cycles, right? You complete, right? 1 over t. That's the frequency.
What's the character you put in?
Huh?
What did you write?
This here?
Yeah.
This is the frequency.
Then F.
Yeah, the frequency is 1 over t. Okay? So,
And the whole thing is a revolution?
Yeah, that's one revolution, right? One revolution.
So
Now-
one revolution is one period.
It's one period, yeah. Now, let's think about now that this is uniform circular motion, right? There is no tangential acceleration here because the velocity is the same. But now, let's make another drawing here. And now velocity is changing from here to there. Now, the magnitude, not only direction is changing, but also the magnitude is changing. So, we do know that we have AC here, right? AC, right? Centripetal acceleration. But now we also have a tangential acceleration, okay? Okay? So now, when we come up from here, from this formula here, look at this formula. There is no tangential acceleration here, right? The magnitude of this velocity is the same, because this is circular, uniform circular motion. But now this here is changing. Okay? So let's bring this here. Now delta V is going to be delta omega R. Okay? Now this one here is changing. It's not constant anymore. So that means there is a delta V. And also, if the tangential velocity is changing, omega is also going to change, right? The rate of change of the angle is going to be faster and faster. Here, every time I would take a picture, 1 second, 2 seconds, 3 seconds, this angle is the same. Do you guys remember here the linear motion? Every picture I take, the displacement is the same. So it's constant speed. Here is the same. I take a picture, this angle, 1 second, 2 seconds later is going to be the same angle, the same angle. You guys see that? You see that here, because this motion is uniform, the angle is going to be the same, 1 second, 2 seconds, right? The angle is changing the same every time I take a picture. But when I have here tangential acceleration, that means this thing is speeding up, going fast and faster. Let's see if I have here. Look, I have this little thing here, so it's going like this, right? So here I'm trying to make it going at the constants. But if I start accelerating, you see that it's going up and up, right? Now this is kind of slow, and then I accelerate. You see that? So I accelerate because I increase here the tangential speed. Okay?
So the centripetal acceleration stays the same.
That stays
Even
the
if you
same.
accelerate,
That's
Yes, sir.
still gonna be, the centripetal acceleration is going to be V squared over R.
but which V?
But, at that moment, right?
Yeah.
V is changing. So that's also, being changed here because they
So
affect
the
each other.
acceleration changes too.
Yeah,
The-
so look here. This here is changing, this is changing. Now if I want to relate to the acceleration, so I divide here by delta t, and here is going to be delta t. Okay? Because I want to know this acceleration now. See? So now this is going to be A, t is going to be alpha r. So here,
What's alpha?
this is the angular acceleration. Because remember, this angle here is not changing, right? So there is no acceleration. There is no angular acceleration. Omega is constant. The rotation is going constant, right? But the moment I increase, right? Now this theta and this one here, this is going to be delta 1, this is going to be delta 2. They're not the same anymore. So the angle is, how fast this thing is going around is changing, so the angle is also changing. First second, second second, third second, you see that the angle is changing from one position, position 1, position 2, position 3, right? From position 1 to position 2. From position 2 to position 3. From position 3 to position 4. So that angle is changing. Every second I take a picture. Okay? I know this is a lot, but when we do the experiment, you guys are going to be able to see that, okay? And then on Thursday, we're going to do some problems too. So now, let's try to figure out this acceleration here, right? The tangential acceleration, right? So if I have centripetal acceleration going this way, and I have a tangential acceleration going this way, so there are two vectors, right? What is the total acceleration? Is the sum of these two vectors. So acceleration is going to be equal to square root
AC plus AT squared. AT squared is C squared.
That's it, okay? Okay? So, with that, I'm gonna stop here today, and we'll